Let us now recap briefly what we've been learning about the electric potential. We've learned, after learning its basic definition, we learned a fairly simple formula for computing it. Namely, if we want the electric potential at some location x, so here in some diagram I have some point x where I want this electric potential, all I would do would be to go and sum over all the charges n in the system, Coulomb's constant times the corresponding charge, and then just divide by the distance to that charge. In the case of a continuous charge distribution, such as some surface sheet that I'm showing you here, the sum would become an integral. We have Coulomb's constant, the charge of any little chunk of my system. In this case, it would be a little patch. And then we divide by this distance r, which represents the distance between the location where you want to calculate the potential and the patch. So this would be that particular distance, r sub n. In the continuous case, the little charges on our little patches, the little q sub n's, we would call dq, and there are a variety of forms for dq depending upon the type of system we're talking about. In the area example down below, it would be sigma, charge per unit area, times the area of the little patch, or it could be lambda, charge per unit length, times the length of a little segment of some line or curved wire, or rho, charge per unit volume, if we had some solid distribution, and we'd be multiplying then by the corresponding dV. In terms of uses for this concept, there were two major uses, and we're actually in the midst of looking at a third use. The two major uses are, first, to get voltages. The voltage to go from point A to point B, recall, is just basically a potential difference. We simply take the potential at point B and subtract off the potential at the reference electrode, the first electrode at point A. We also saw, leveraging off of this result, we were able to prove, in fact, that we can recover the electric field very easily by taking the gradient of our electric potential, where we reviewed the definition of the gradient from your multivariable calculus classes. The beauty of this whole setup is you'll notice to calculate potentials, although we may have to do integrals, there's no more sines or cosines, there's no more trig form, there's no more Cartesian form, but yet we are still able to compute electric fields, and we can recover that vector nature simply now by taking derivatives. A very powerful method. If you can pull it off, it's much more convenient than actually calculating electric fields the old-fashioned way.